In this video, we're going to calculate pH changes from the titration of a strong acid and a weak base. Initially, we'll calculate the pH of this weak base. It's going to be ammonia. When I write the equation for a weak base, I do need to put water in. Specifically, it's the nitrogen on the ammonia molecule that's really attracted to hydrogen. He's going to rip one right off the water molecule. So we'll be left with NH4 plus. And here's the hydroxide. We know it's supposed to be a basic solution, so we're looking for hydroxide. It comes from the water. Now we can kind of set up a little ice table. The initial weak base is 0.050 molar. We're not going to use the water in our calculations. And initially our products are 0. But they can't stay that way at equilibrium, so we know that this is going to shift forward by x. So this will be 0.050 minus x, x, and x. Now we just got to solve for x and we're done. They give me the Kb, since this is a weak base, 1.8 times 10 to the negative fifth equals x squared over 0.050 minus x. That k is small, so I will not hesitate to use the 5% rule. We can cross multiply, take the square root. I get x. I guess we can leave 2 sig figs. Let's say 9.5 times 10 to the negative fourth. Of these two products, the x that I'm really concerned with is the hydroxide. That's the sign of a base. So it might be easiest to take the POH, which would be opposite log of the hydroxide concentration, 10 to the negative fourth, molar hydroxide. And I get about, weird, 3.0. So if I subtract that from 14, I can get the pH. Let's just call it 11. If we just leave it at 2 sig figs, I'm okay with that. Makes some sense. It should be a base. I'm looking for a pH greater than 7. I'm okay with that. All right, now let's start titrating, huh? We've got 100 milliliters of this weak base. We want to know the pH after the addition of 25 milliliters of 0.1 molar HCl. So now, just like what we did in the other titrations, I would redo those molarities right away, so you don't forget it. It's just the dilution equation. It's not hard, but it's probably one of the most common mistakes at the end of a titration problem. So let's redo these right away. What do we got? I don't know. We could do the base first. The base comes first, I guess. Originally, the base, in the previous problem, what was it? 0.05? 0.050 molar. We're starting with 100 milliliters. I want to know the new molarity when we add 25 milliliters of acid. So the final volume becomes 125. M2. How about 0.040? There's the base. We can leave 2 sig figs. The original molarity was 2. I'm okay with that. Then we'll do the same thing with the acid. The original acid is 0.1 molar. Originally, we have 25 milliliters. I want to know the new molarity at 125 milliliters. M2. How about 0.020? Nice. All right, I'm ready for my ice table. I need an equation. So I've got the weak base. I can't like dissociate that, break that down any. That's just going to stay NH3 ammonia. I'm adding to that hydrogen chloride, a strong acid. Eventually, the chlorine is just a spectator, so you can leave him out of your net ionic equation in a sense. We're going to have that NH3 ammonia reacting with the hydrogen. On the product side, we're just going to have ammonium, the ammonium ion. All right, this is good. ICE. Let's see what we have. My ammonia concentration is now 0.04. And my hydrogen from the acid is 0.02. Initially, I do not have any of this product, the ammonium ion. So in a sense, this is kind of the stoichiometry part. I want to react these two reactants as completely as possible. One of them is probably limiting. It should be the one that's smaller. In this case, the hydrogen. Let's get rid of it. We'll bring it down to 0. Everybody else reacts accordingly. So this is going to go down by 0.02. Ooh, so that'll be 0.02. And this is going to go up. 0.020. 0.020. And you could put these in as molar solutions if you wanted to. All right, so we want to find the pH of the solution. We've gotten rid of the hydrogen in exchange for the formation of a little ammonia. Well, this might ring a bell to you. Look what's left. Are you jumping for joy that this is a buffer solution? This really is just, in a sense, a classic buffer. You know, we added some strong acid hydrogen, but the buffer was able to absorb that hydrogen because the original molarity of the weak base was greater than the hydrogen. In exchange for the hydrogen, we formed a little ammonium, which is a weak acid. What's left in the solution is the weak base and his conjugate acid. That's a buffer. We have a basic buffer solution. Now, there's a couple ways you could do the pH. I kind of like to use the Henderson-Hasselbalch, but the basic version is not in your packet this year. I don't know why, but it's pretty easy to switch the acidic version to the basic version. It's just POH equals opposite log of the KB, which they gave us originally. I think it was 1.8 times 10 to the negative fifth. So this is the KB plus the log. And it's really similar. It's always the log of the charged particle over the neutral particle. The conjugate over the original acid or base. In this case, we don't really care because they're the same. They're both 0.02. Technically, this would be the NH4. And this would be the 0.020 molar NH3. So it's always the charged particle over the neutral particle, which they kind of show you in the AP packet when they give you the acidic version. It's really similar if your buffer is a base. You'll just be using the KB, and that'll give you the POH. Now, if you wanted to, you could recalculate the Ka and plug it in, and it would be fine. But I think this is kind of just as easy. So if I plug it all in, I get about 4.74. That's the POH. So then we can just subtract that from 14 to get the pH. So I might say my pH is what, 9.26? Oh, I like this. Because again, this is the essence of a buffer. The original solution started at a pH of 11. We added some strong acid hydrogen. Did the pH go down? Yes. but not that bad. We went from like an 11 to a 9. If I would have added that hydrogen to water, the pH would have gone crazy. So this was a nice little basic buffer. The other thing that we should mention, what you have right here, this is called the halfway point. This is called the halfway point in a titration. We started with the ammonia and we added hydrogen from the acid. At this point in the titration, we're halfway to the equivalence point. At the equivalence point, these two would be equal. We would have equal amounts of base and acid according to the balanced equation. We're halfway there. So if you ever see that term like the halfway point in a titration, essentially this is kind of what they mean. The point where you've added half as much of the hydrogen or hydroxide as the original solution. If you were graphing this, they didn't give us a graph of this originally. This is going to fall into the buffer zone. Now, this one, I think we're starting with the base and we're adding the acid. So the pH is actually going to kind of like drop as we curve down. Well, these parts where like the pH is rarely changing, or I mean just barely changes, and we're still adding strong hydrogen, strong acid. This is the buffer zone or the buffer region where the pH doesn't change by much. This halfway point really is kind of like halfway to the equivalence point. So if this was the equivalence point, like right in here, this would be like the halfway point. It's going to fall in the buffering region. So like if I look at what I had after my ice table was complete, I did have a buffer. I had the weak base and its conjugate acid. So the halfway point will fall in the buffer zone. But it really is like halfway to the equivalence point. The other thing that we should make note of, at the halfway point, you might have noticed this, and this is always going to happen. The P, in this one we could say the pKb will equal the pOH. Or if it was an acidic solution, opposite log of the Ka is the pH. If you're at the halfway point and you do your ice table, you're always going to have like equal amounts of base and conjugate acid, or acid and conjugate base. So this ratio here is always going to end up being the log of 1. So if you are at the halfway point, this will always hold true. If this would have been an acidic solution, maybe my graph would have kind of looked like this. Like if I was adding the base, it would be kind of opposite. So this might be kind of like my halfway point, and maybe this is like my equivalence point. Maybe this is like my halfway point. It does still fall in that buffering region where I'm adding strong base and the pH isn't changing dramatically. But with your calculations, that will always hold true. After your ice table, if you recognize that you're at the halfway point, your pH will just be opposite log of the Ka, or your pOH will be opposite log of the Kb. And that's kind of why this ratio at the end will always end up being 1. All right, let's take a little breather. Go get a snack or take a little break, and then we'll do the last two.